Well, one application of the derivative, you guys, is finding minimum and maximum values off of a graph. In pre-calc, we could always find like the minimum, or if it was flipped over, we could find the maximum, right? Because it was always on our axis of symmetry. So if it was in standard form, it was x equals negative b over 2a. We could find that. That was no problem. But the problem with pre-calc or static mathematics is you can't find these on, let's say, some fourth degree polynomial, right? You can't find those without calculus. You got to use calculus to find where the derivative of the tangent line is 0, right? And so that's what we're going to get into, is we'll talk about extrema today and local extreme values. So let's start with that discussion to kind of gauge your memory a little bit with some pre-calc for a second. If you have a minimum, right, that would be like bottom of a valley. So like right here, notice we've got a minimum on there. And there's a difference between minimums, absolute minimums, and relative minimums. Absolute minimum means on the entire domain, is it the lowest point? And in this case, it is. It is definitely the lowest point on the entire domain. So that would be an absolute minimum. A relative minimum means just in an area. So like this would be a relative or local minimum, but this one's actually the lowest. So this would be the absolute minimum, right? This would be a local minimum. And any absolute minimum is also a local or relative minimum as well. Okay. Now this one obviously goes up and up, so there's no highest point, but you do have a relative or local maximum right there, meaning in that area, if I just look in that area, it is the highest point, right? So let's go back to these graphs and let's discuss these situations. So this one's an absolute minimum. And if you notice, this is on a closed interval. So notice at f of -1, I have the value of 2. At f of 2, I've got the value of 5. So this is the maximum or absolute maximum. It's absolutely the highest point on that domain. Now the second one is open. It's an open interval, right? It's not a closed interval. It's an open interval. So that absolute minimum is still the lowest point. It is absolutely the lowest point on the interval. But notice I say no maximum up here. Why is that? Well, 4.9 is on there. But isn't 4.99 on there? I could go a little higher. I could go 4.999, right? I could go a little higher, 4.99999. There's always a little higher. There's no highest, because it's open. Does that make sense? So there is no maximum on that one. There's no maximum. How about this one where we close it, but we open up that bottom? So similar discussion with the bottom. I can get a little closer to 1, let's say 1.1. The 1.1's like right here, but that's not the lowest point. I can get a little closer to 1, 1.01. It's a little closer, 1.001, a little closer. Again, I never get lowest because it's not defined there. It's open. I never get lowest. I can always get a little lower, but never lowest. Does that make sense? So that's why you do not have a minimum. It's open. So I'll never get lowest unless it's not defined there. Do I have a maximum? Yes. And this is actually our absolute maximum, right? That's the highest point on the graph. Let's look at another one here. I always like to think about hills and valleys, right? So with local or relative maximums and minimums. So this one is on a closed interval. So this right here would be our lowest point. That's our absolute minimum. But here we have a local. You'll also refer here these also refer to as a relative minimum, local or relative. Meaning if I cut off the graph and just looked in that point, that's the lowest point in the area, right? Relative or local minimum. All right. So here we've got a local maximum, or again, relative maximum is the same thing. But that's not the highest point. This is the highest point right there. There's our absolute maximum. That's the highest point on the graph. And then over here at the end point, we do have a local minimum. So we could, you know, if we cut this off, we could say, well, if I just look in this area, that's my lowest point in the area. So it would be a local minimum or relative minimum. Okay. All right. Let's talk about critical numbers. Critical numbers will help us to find where these relative minimums and maximums are. So actually, let me go back to this for just a second. Let me erase all this junk. Notice at the local maximums, all my derivative, the slope of the tangent line is 0. The slope of the tangent line is 0. Or it's at an endpoint, or they occur at an endpoint. Or, see how you got a little sharp cusp right here? Well, at a sharp point, the derivative is undefined, because the limits disagree from both sides, right? At a sharp point. Remember, you got to be smooth to have a derivative, right? Smooth and continuous. So those are going to be where we have a critical point. So what we're going to do is we're going to find our critical points where the derivative is 0 or the derivative is undefined, as long as the point is defined in the original function there. Those will be our critical points, and then we'll evaluate them at those critical points to see if they're an absolute min or max, or local min max, and so on. And that will be our discussion. Okay? So this is our definition. X equals c is a critical number. Either of the following occurs. Derivative is undefined. Like this, we got a sharp point. That would be where the derivative is undefined. Or if the slope of the tangent is horizontal, right? The derivative is 0. And the original function's got to be defined there. Is a qualifying to be a critical point. Okay. And if you think about, I don't want to spend too much time on the absolute value, but the absolute value f prime is not defined at x equals 0, because the slope from the right is 1 and the slope from the left is -1. They don't agree, right? So they're not defined there. They have a sharp point. Right? They have a sharp point there. So let's go ahead and use this approach to find extrema. So what we're going to do is we're going to take the first derivative, say it equals 0, and also see where is the derivative equals 0, and where is it undefined? Where's the derivative equals 0? Where's it undefined? That gives you a potential extrema. And then we'll evaluate the original function at those critical points and at the endpoints, and then we'll analyze. Okay, we'll find. So let's do those steps here for this first one. Okay, here's our function. We got a 4th degree function. Let's find our critical points. So where is the derivative equals 0 or undefined, as long as it's defined in the original function, right? So here's the f of x, here's our original function. Let's take the derivative. 3 times 4x cubed, so I got 12x to the third plus 12x squared minus 24x. I'm going to find where the slope of the tangent is 0. So where's the derivative equal to 0? Notice I can take a 12x out of each of those. And I can keep factoring where's the derivative equals 0. And then I take each factor, set equals 0. Divide by 12, subtract 2, add 1. And that's where the derivative is equal to 0. Notice I don't have anywhere where the derivative is undefined. Okay. The derivative would be undefined. Let's say if I ended up getting the derivative and it was something like this. And I say, oh, the derivative is undefined at -3. Okay. That would be an example of where the derivative is undefined. Okay. So this one, the only critical points are listed right there: 0, -2, and 1. And so that's our step 1. Find our critical points. And then what we want to do is we want to evaluate it, step 2, at each critical point on the interval. So step 2, let's plug those in and evaluate them. So I have -2, 0, and 1. And I also want to do the endpoints as well. My endpoints, because this is going from the closed interval from -4 to 2. My endpoints might also be absolute minimums or absolute maximums. Okay. And then we're just going to plug them in one by one on this, right? So here's my original function. F of x is 3x to the 4th plus 4x cubed minus 12x squared. Let's throw in 0. I'll do the 0 first. I get 0. That's an easy one. Looks like I got 0. Now let's do the 1 next. F of 1, I got 3 times 1. So -5. Anyways, I keep going with this. F of -2. Plug all these points in. Blah, blah, blah. Let's see if I got it. It'll be 32. And then I do the endpoints as well. So I plug in -4, 20, plug in the 2, you get 32. Okay. And then I say, all right, well, what's my highest point? My highest y value here would be that 320 for sure, right? So this is the absolute max. And what's my lowest point? Well, this y value right there, there's my absolute min. Okay, so let's state it now. The absolute max of 320, and it occurs at x being -4. And then we have an absolute min of -32 that occurs at x being -2. And those are our absolute extrema on this closed interval. All right, let's do some more here. Let's go ahead and... All right, so for this one, it looks like we've got our function here is 12. I'm going to write that as x squared to the 1/3, so x to the 2/3 minus 8x. And let's go ahead and number 1, let's find our critical points. So where's the derivative equal to 0, and where's the derivative undefined? And then make sure they're defined in the original function at those values. So we got 12, we got 2/3 x to the 2/3 minus 1, so -1/3 minus 8. So it looks like I got, what's that, 24 to 8 over, or 8x to the -1/3 minus 8. In other words, 8 over the 3rd root of x minus 8. There's our derivative, right? So hopefully you notice that, oh, the derivative is undefined if, yeah, x is 0. So let's note f prime is undefined. Can't divide by 0 when x is 0, okay? Now, I do need to make sure, is this a critical point? Well, if I plug it into the original, I can take 0, square it, and then take a 3rd root of 0. That's fine. It's defined in the original. So it is a critical point. Yeah, I got to make sure that the critical point is defined in the original function, and it is. Now, we also want to make sure, besides where's the derivative undefined, where's the derivative 0? So 8 over third root of x minus 8. Let me add 8 to both sides. So I have 8 equals 8 over third root of x. Multiply both sides by third root of x. And let me divide both sides by 8. So I have third root of x. Come over here. Sorry to make a mess of this. Third root of x equals 1. Let me take the third power. So x is 1. Is my other critical point, right? So my critical points were x equals 0. That was where f prime was undefined. And x equals 1. That was where f prime equaled 0. And notice if you plug 1 back into the original function, it is defined in the original function. So both of these are critical points. Let's go on to step 2. I want to plug these in. 0 and 1. Don't forget my endpoints, -1 and 2. I've got to check those two. And I'm just plugging these in one by one. Let's plug the -1 in. 12 into the original function. Third root of 1 is just a 1 plus 8, so it looks like I got 20 here. Plug the 0 in. Looks like I got third root is 0. That's just 0. Plug the 1 in. That'd be 12 minus 8. I got 4. Plug the 2 in. 2 squared 4. 12 times third root of 4. Oh, that's kind of a mess. So I got 12 times 4 to the 1/3. I'm going to punch this in, minus 16. I give you 3.05, 3.05. Okay. So where do we have, notice it's asking for the absolute extremis. So the absolute highest point would be right there. Absolute max. And our lowest would be at 0. There's our absolute min. So let's go ahead and state this. We have absolute max of 20. It's the functional value, and it occurs at x being -1. X being -1. We have an absolute min, the lowest point on the interval, from -1 to 2. The absolute lowest point is 0. Oh gosh, what did I do? At x being 0. And there's our solution for that one. We've got the secant now, so let's go ahead and take the derivative to find our critical points. So derivative of secant, secant, tangent. And if you think about that, that's 1 over cosine times sine over cosine, right? So where is the derivative undefined? Well, anytime it'd be undefined, f prime would be undefined, anytime the cosine's 0. Well, cosine of what is 0? And hopefully you say cosine of pi halves, right? And I'm only looking between -pi6 and pi thirds. So this is actually outside of that range anyways, but I'll make a note of it. Now, where is it 0, right? Where is this true? Where is f prime 0? So I have sine theta over cosine squared theta. Well, I just got to get the sine of theta to be 0. 0 over anything would be 0, right? So if the sine of theta is 0, then this is true story, right? Well, sine of what is 0? Hopefully you say sine of 0 is 0. I also know the sine of pi is also 0, 2 pi, and so on, right? But those are outside that -pi6 to pi thirds, right? So this was step 1. These are my critical points. Put them on my graph. I have 0. I have the pi halves But notice I'm only going from negative pi 6 to pi thirds. This is outside, so I'm going to forget about that pi halves where it was undefined. It's outside my interval that I'm examining. Right? So then I just got to plug in and check those three, negative pi 6, into my original function. So here's my step 2. Let's go ahead and check them. So f of theta, my original function was the secant of theta. So f of negative pi 6, secant of negative pi 6. So I'm looking on my unit circle at negative pi 6. Oops, that's positive, negative 1/2. And the secant's 1 over the cosine. The cosine there is root 3 over 2, so this just ends up being 2 over root 3, or 2 root 3 over 3. Or you could punch that in and get 1.15. Then we'll do that for 0. Well, that's 1 over the cosine of 0. The cosine of 0 is 1, so that's 1 over 1. And then we'll do that for pi thirds. We get 1 over the cosine of pi thirds, which is a half. So 1 over 1/2 is 2. Right. I say, well, what's my highest point here? It looks like 2. There's my absolute max. And what's my lowest point? There's my absolute min. So let's write it absolute max of 2 at, where does it occur? Pi thirds. Absolute min of 1 at x being 0. Let's move on here. Let's do a transcendental function now. Let's find our critical points by taking our derivative. So f prime of x, we got the ln of e negative x squared chain rule. Derivative of negative x squared is negative 2x. Ln of e, of course, is just 1, so this just ends up being negative 2x e to the negative x squared, or negative 2x over e to the x squared. That's our derivative, right? So then the first discussion is, well, where's this undefined? Where's f prime undefined? Well, if I can get this to be 0, that'd be undefined, right? Well, e to the x squared, x squared is always going to be positive. So e to anything, will it ever be 0? If you think about the graph, whoops, oh no, there we go. Think about the graph of e to the x, right? There it is. So e to the x squared is just, again, I'm not sure exactly what that graph looks like, but it's always e to a positive value, right? So it's always going to be positive. Another way to think about this is if you're solving this algebraically, you would take the natural log of both sides. Ln of e to the x squared is x squared, so you're trying to solve for this x. Well, you punch in the natural log of 0. If you think about the natural log function, here's the natural log function. There is no natural log of 0. This is undefined. So there is no place where the derivative is undefined here, because e to the x squared will never be 0. We can never get that to be 0. All right? So let's move on and just examine the critical point where the derivative is 0. How about this? Well, as long as we can get negative 2x to be 0, we know the bottom's always positive, right? So where is this true? Well, divide by negative 2 at x equaling 0, right? So that's got to go on our xy, that x value. Don't forget these endpoints, negative 2 and 1, when you're looking for these absolute extrema, right? And we'll go ahead and we'll plug it into the original. Here's our original e to the negative x squared. In other words, 1 over e to the x squared. Let's plug in negative 2. Get 1 over e to the negative 2 squared. So 1 over e to the 4th Plug in 0. 0 squared is 0, so e to the 0, anything 0 power is 1. I got 1 over 1. Plug in the 1, you get the 1 over e. So our highest point, remember e is 2.718, right? E is 2.718. So our highest point would be that 1. So our absolute max of 1, it occurs at x equals 0. And our lowest point here would be that 1 over e to the 4th, right? That would be our absolutely lowest point. So absolute min of 1 over e to the 4th, whatever that is, at x being negative 2. I'm going to go ahead before I do this and write this as 2/3 x plus 5/3. Then let's go ahead and find our critical points here by taking the derivative. You got 2/3 plus 0. Well, where is this undefined? Nowhere. Where is the derivative equal to 0? Nowhere, right? So we have no critical points. There's no critical points here. And so you just go straight to the endpoints. Throw that negative 1 in for x into the original function. So 2/3 times negative 1, negative 2/3 plus 5/3, 3/3, or 1. Put the 5 in. 2/3 times 5, you got 10/3 plus 5/3, 15/3, or 5. So here's our absolute max. There's our absolute min. Of course, you know, if you were graphing this, it looks something like this. And you're looking from negative 1 to 5. So, of course, being a line, that's your lowest point, and that's your highest point, right? Pretty obvious, but we just want to walk through, make sure with our calculus critical points there. Let's go ahead and find the extreme values, both absolute and local, actually, of the function over its natural domain. So we got f of x being 2 over x squared minus 1. Let me write that as 2x squared minus 1 to the negative 1 before I start doing step 1 and finding my critical points. So now I take the derivative. So the 2 would stay there. Run the power rule, negative 1, x squared minus 1 will now be to the negative 2, and then the derivative of the inside chain rule 2x. So I got negative 4x over x squared minus 1 quantity squared. That's my derivative. And then I look at this, I'm like, well, where's the derivative undefined? Where is it undefined? Well, if we can get this to be 0, it'd be undefined, right? That's square root, both sides. So I'd have x squared minus 1 equals 0. I factor that. So it looks like x being 1 or x being negative 1 would be where this would be potentially undefined, right? Now, I said it's a critical point as long as it's defined in the original function. So these appear to be critical points, but if you notice, if I plug 1 back in to the original function, see how it's undefined? It's undefined at x being 1. So I got to throw that out. Well, guess what? I throw negative 1 in, and the same thing happens. So I can't even consider them at all because they're not defined in the original function, right? Yes, they were undefined in the derivative, but they weren't defined in the original function, so they can't be a critical point. They have to be defined in the original function to be a critical point. All right, so how about where's the derivative equal to 0? Well, we have the derivative here. Here's my derivative. Where's the derivative equals 0? Well, as long as the numerator is equal 0, we're good to go. Divide by -4. Okay, x equaling 0. If I throw x being 0 into the original function, right there, does it work? Yeah, it's defined. 2 over 0 squared minus 1 is 2 over -1, -2, right? So yes, it is defined, so we can consider it to be a critical point. So we'll throw it in for analysis. 0, don't forget, oh, this is over the natural domain here. So in this case, if you think about 2 over x squared minus 1, that would have, let me go back to pre-calc for a minute. Here's my original function. Let me factor the x squared minus 1. So hopefully you can see, oh, I've got vertical asymptotes where this is undefined. I have vertical asymptote there. I got a vertical asymptote there. So graphically what's going on, I have these two vertical asymptotes. I have a horizontal asymptote of y equals 0, and then you could plug in a bunch of points if you wanted to. I'm just going to make this visual so you can kind of see my numeric analysis on this as well. So the domain is everywhere except at -1 and 1, right? And what I'm looking for is any absolute maximums. Do I have a highest point? Well, no, because these things just keep going up, right? I'm not going to have a highest point on this. There's not going to be an absolute max. I know I kind of gave it away with the graph here, but we'll go back to the numbers in just a second. But do I have a local max? Yes, I do. Right there at 0, right? And I would plug that into my original. I'd get, oh, that's the point 0, -2. I can't throw in -1 or 1. They're not even defined there. So I kind of want to see what's going on around it, right? If I didn't have the picture, I would plug in points around 0 and see if it's a highest point or a lowest point. And so I'd throw in like maybe -0.5. So I have 2 over -0.5 squared minus 1. So 2 over 1/4 minus 1, 2 over -3/4. And I'd get that -2.6, -2 2/3. I'd throw in like a half on the other side. And guess what? I get the same thing. I'm like, oh, it's lower. So this has got to be a local max right there at that critical point, right? And that's how I'm kind of thinking about that. So it's a local max or a relative max at of -2. It occurs at x being 0, and that's kind of how I'm thinking about that. All right, let's find our extreme values, our absolute local and local, absolute and relative of the function over its domain where they occur. So let's go ahead and take the derivative here. So notice our u here is that e to the x, right? And if you remember, when y is arc cosine of u, then y prime was 1 over the square root of 1 minus u squared times, oh, I'm sorry, -1 over 1 minus u squared, let me make sure I'm writing that right, times u prime. That was our rule, okay? So let's go ahead and take that derivative. We got -1 over the square root of 1 minus, our u is the e to the x squared, and then times the derivative of e to the x. Well, that's ln of e to the x. So we got negative e to the x. Remember, ln of 1 is just 1. Over 1 minus square root of 1 minus e to the 2x here. First of all, where's this thing undefined? Where's f prime undefined? Well, anytime this square root of 1 minus e to the 2x is 0, can't divide by 0, right? So let's go ahead and square both sides. 1 minus, so it's 1 minus e to the 2x equals 0. Let me add 2x to both sides. So I have e to the 2x is 1, or 1 equals e to the 2x. Let me undo with the natural log here. ln of e to the 2x, we'll undo that, get 2x. Natural log of 1 is 0, divide by 2. So it looks like x equaling 0. Let me make sure it's defined in the original. I go ahead and plug it into the original. E to the 0 is 1, and the arc cosine of 1 does exist. So yes, x equals 0 is a critical point. Now I go to, where is this thing equal to 0? Where's the derivative equal to 0? Well, anywhere. Where's f prime equals 0? If the numerators equals 0. Let me divide both sides by negative 1. So I have e to the x equals 0. Let me take the natural log. Natural log of 0 does not exist. So there's nothing from the derivative being 0. So we can only examine around 0, right? Now what I'm going to do here is I'm going to take a look at values as I shoot out from 0 on this, okay, and actually approach 0 from the left, okay. So like let's say I throw in negative 1, negative 2, and then I'll just skip a bunch like negative 10, negative 100, and so on. I punch those in. Let me pull up my decimals here. I should put in, let me pull up decimals. Sure, meridians here. Let's see, where's my arc cosine? Let me throw in the 0 first. Oh, I'm sorry, e to the 0, good grief. E to the 0. There we go. Which is arc cosine of 1, which is 0. So I'll put that in, write that in. That one ends up being 0. Come on, there you go. Go back, let me throw in negative 1. .19. Put in negative 2. I'll punch that one in. Then I'm going to put in a negative 10. See how that's 1.57. And I'm going to just keep getting big, big, big. So I'm going to jump to negative 100. Let me write those in. 1.57. And hopefully you start seeing, oh gosh, these are, I know they differed after that, right? I rounded that to the 10,000th there. But as I shoot out, right, as x is getting smaller and smaller, I'm shooting to negative infinity. See how it's approaching pi halves? So this thing's actually going to have a horizontal asymptote at y being pi halves, that 1.57, right? Now the problem with punching in something bigger than 0 is that arc cosine is restricted See how it's undefined if I go to the right of 0, so I can't even examine that. So I'm just stuck with, let me pull this back up. Restricted right to there as my absolute min, because I can't go to the right. It's not defined. If you think about the arc cosine, it's only defined between -1 and 1, right? I know we have the arc cosine of e to the x, but that's going to restrict us to not being able to take values larger than 0, because e to the 0 is 1. That's as far as we can go with that input on the arc cosine. Okay, so we just got the absolute min of 0 at x being 0. All right. Thanks so much for watching. See you next time.